So if there's no more questions, I'd like to move on to our next topic. So I would like to revisit beats. Okay. So we did this at the end of lecture Tuesday, and it was really cool. We showed the tuning forks, so we had slightly different frequencies. We actually heard the wah, 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 right? So that was neat. But now I want to pose a different question to you. What if the speed of the wave depended on its frequency? So I have a little applet for you. Let's see if this will work. Hold on with it now. There it is. I have one set up. Okay. So here are two waves. And you see that in the equation here, it's x minus vt. And so they both have the same speed. But you notice they have different k's, which means they have different frequency. Okay? So let's go ahead and start this. See, okay, this is cool. We see the beats, but it just moves along, and the actual shape of the beat doesn't seem to change at all. So, because it's hard for me to type while looking at the screen, I set up another tab here. Let's imagine now that the k vectors are relative to one another, the same as they were in the last tab. But now what I did is I changed their relative speeds. Ready to see what happens? Whoa. Okay. So what you see here is that the carrier wave, the high frequency signal, is moving at a different speed than the wave packet. Okay? It's moving at a different speed than the envelope. So let's go ahead and do this mathematically and see how this comes about. Are you guys excited? Yeah. All right. Oops, let me get that up here. And there we go. Okay. So let's go back to when we talked about beats. Except for when we talked last week, a couple days ago, I said, well, let's just do it at x equals 0, just to make our math a little easier. Today, let's not do it at x equals 0. Woohoo! Okay. So we're going to have two waves. The first one, let's say that it has a slightly higher frequency. So it's going to, instead of having a frequency omega, it's going to have omega plus delta omega over 2. The same little trick that we did last time. Except for now the k vector changed as well. So it's going to have k plus delta k over 2 times x minus omega plus delta omega over 2 times t. Okay, and then our other one is going to be shifted down by delta omega over 2. Did I lose any parentheses? Good. I think I'm good. Okay, so we're going to have k minus delta k over 2 times x minus omega minus delta omega over 2 times t. Okay. Now, what I'm going to do is we could go through this with a bunch of trig identities. But I promise you, this is so much easier if we do complex exponentials. So that you're going to see, it's going to be really elegant. Okay. So let me remind you of the fact that e to the I x is I sine of x plus cosine of x. Right? Okay. So that means if I want to write a sine of some junk, I can just write it as the imaginary part of e to the I some junk. So that's what I'm going to do. So I'm going to pull out my amplitude. And I'm going to say it's the imaginary part of e to the I this. Okay, I'm just going to multiply out all these terms. Can you Can you guys see this in the back? Is that okay? Okay. So we're going to have kx plus delta k over 2x minus omega t minus delta omega over 2t. Okay, so that's the first term, plus e to the I this. So that looks like kx minus delta k over 2x minus omega t plus delta omega over 2 times t. Okay, the reason that complex exponentials are nice is we can look and say, do they have anything in common? And it looks to me like they both have an e to the I kx minus omega t. So I'm going to pull that out. So they all have an e to the I kx minus omega t. Okay, now what's left over? This guy has an e to the I delta k over 2x minus delta omega over 2t plus this guy has an e to the I. You know what? It's negative delta kx over 2. I'm going to pull out a negative. Okay, so this makes this delta k over 2x. And I pulled out a negative, so this has to be a negative. So negative, negative makes a positive. Okay, does anybody recognize this is e to the I junk plus e to the minus I junk? What is that? Is it sine? Is it cosine? It is 2 cosine. So this right here is 2 cosine of junk. And if you stare at that long enough, I bet you'll be convinced of that being true. Okay. Okay. So this is 2 cosine junk. So I'm going to bring out my 2a. I still have my imaginary. Okay. Let me do this first. Let me write this back in terms of sines and cosines. So this is I sine of kx minus omega t plus cosine of kx minus omega t. Okay, so that's this part. I need another parentheses. Oh, we can get all crazy. Okay, this one I said was 2 cosine of junk. So I had my 2. So now I need my cosine of delta k over 2x minus delta omega over 2t. All right. What happens when I take the imaginary part of a real thing? Gone, right? What happens when I take the imaginary part of an imaginary thing? It gets the thing, right? Okay, so let's write what we finally get. We're going to get 2a. Imagine part of this, we get sine of kx minus omega t times cosine of, I'm going to pull out a delta k over 2 just for fun. Because then I get x minus delta omega over delta k times t. Ooh. Ooh, you know what? For fun, let me do that same trick right here. Is that okay? I'm just going to, sorry guys. Am I good on the parentheses? Okay. Why in the world did I do that? Oh, define velocities, because you guys just did this in your cat and hat problem. But then we were talking about the waves. We get them, the waves we talked about, we get them in the form x plus vt or x minus vt. So if you have something x minus some junk t, that some junk here for a wave is going to be the velocity. Now we have to talk about what the heck these velocities are. Okay, so this, let me see. I'm going to say that this guy, he's oscillating at a nice, fast frequency, right? He's oscillating at omega. So I'm going to say that this is our carrier. What is the speed of this carrier wave going to be? It looks like V, I'm going to call this phase, and we'll talk about this in a second, is this thing, omega over k. All right, this guy is our envelope. This is the thing that made the wahs. Okay? Yep, exactly. Okay, and this is going to be called the group velocity. It looks like, what's our group velocity going to be? Delta omega over delta k. What if those deltas get really, really tiny? Well, what do the deltas become? D's. So we're going to get V group, V omega, dk. Okay.